This is a single pendulum, and through the laws of physics, it's entirely predictable. Give me its mass, its starting angle and its angular velocity, and I can tell you exactly where it will be 1,000 years from now. But what happens if we add a second pendulum to the bottom of the first one? The order disappears and chaos follows. This is a double pendulum. It's a deterministic system, meaning it follows strict physical laws, yet its long-term behavior is completely impossible to predict. Today, we are going to build this simulation from scratch. We will look at the simple geometry behind it, implement the physics equations in Java, and finally simulate 100 of these pendulums at once to watch chaos unfold. Welcome to this episode of Dev Journey. To build this, we don't need a PhD in theoretical physics. We just need to know where our joints are on the screen, and for that we use simple high school trigonometry. Let's look at the first pendulum. If we know the length of the arm and the angle it forms, we can use the sine and cosine formulas shown on the screen to find the exact x and y coordinates. But how do we find the position of the second pendulum? It's surprisingly simple. We just calculate its offset using the exact same trigonometry and then add it to the position of the first pendulum. Now, how about the movement itself? To figure out how fast the angles change, we need angular acceleration. And if you look up the physics equations for a double pendulum, you'll find this absolute monstrosity. It looks intimidating, but don't worry, you don't need to understand it, because we don't have to derive it by hand. We just put it into code and let the computer do the heavy lifting. So let's do exactly that and write some code. Let's set up our Java class. Read a few core variables for each arm, their lengths, their masses, and most importantly, their current angles and angular velocities. Remember that scary equation we just talked about? We break it down into smaller, manageable chunks in Java. It's just a lot of basic math operations, multiplication, addition, and some trigonometry. Conceptually, we are just calculating a single number, the acceleration. Once we have the acceleration, we use a basic concept called numerical integration. We add the acceleration to our velocity, and we add our velocity to our angle. A physics engine is now complete. Finally, we translate our physics into pixels using the trigonometry we discussed earlier. We calculate the x and y coordinates, draw lines between them, and render our circles off the canvas. Now that our simulation works, let's look at some chaos. I have spawned two pendulums here. Their starting angles differ by exactly 0.001 degrees. At first, they seem completely identical. They swing in perfect unison. But give it a few seconds, and they completely diverge. This is sensitive dependence on initial conditions, or the butterfly effect in action. So, what happens if we simulate 100 pendulums at the exact same time, each with a microscopic difference? Well, we get this. It's crazy how a few simple lines of code can create this level of complexity. Everything in the simulation follows strict fixed physical laws, but after just 10 seconds or so, all predictability goes right out the window. Change the starting setup by the smallest amount imaginable, and you get a completely different pattern every single time. Thanks for joining me on this dev journey. If you enjoyed the video, consider giving it a like and subscribing to the channel if you want to see more of this in the future. Thanks again for watching, and I'll catch you in the next one.